Topic Notes 9.1 Tides and Currents. You are looking at one of my favorite places in Palm Beach County, and that is at Munyon Island. And of course, estuaries can be very different between low and high tide. This picture was taken towards low tide, and of course, you can see there's some sandbars out. Boaters will definitely know that you have to pay attention to tides, especially in coastal regions where sandbars and shallow areas can really become a problem. So today we're going to talk all about tides, and of course we're also going to add on currents. So here are your big ideas for this note set. First of all, tides are formed from the gravitational pull of the moon and the sun and are different across the globe due to a variety of physical factors. Then moving on to currents, surface currents are caused by the interaction of global wind patterns and the ocean's surface. Deep water currents are caused by variations in density and form a global conveyor belt that redistributes things like heat and nutrients. As always, here are your learning goals, which can also be found on your topic focus sheets on the learning scale, so make sure you're paying attention to those as we go along. So we're going to start with the concept of a tide. Now, as stated here, tides are the periodic rise and fall of the surface of the ocean resulting from the gravitational pull of the moon and the sun. Now, of course, there's a lot more to it than that. The diagram here gives you some basics. Now, first, notice the central dot in the middle of the Earth. Also notice the center of mass of the Earth and the moon together. These two dots are not the same. As the moon rotates around the Earth, that center of mass is going to rotate as well. Now check out that arrow pointing towards the moon that says the gravitational force. It's a bit easy to understand how the water on the Earth is actually attracted to the gravitational force of the moon. Now note that there's another arrow pointing away from the Earth on the opposite side from the moon. This also represents another tidal bulge, and it's labeled centrifugal force. If you've ever been in the gravitron at the fair, you'll note that you're pushed against the wall as the machine spins. That's pretty much a centrifugal force. It's that same force that causes the second tidal bulge on the side of the Earth opposite the moon. Now, as the moon rotates around the Earth, both of these tidal bulges will rotate as well. Now, the Earth has a variety of tidal patterns, and here are the three main ones. There's semi-diurnal, which means that particular location has two high and two low tides each day. Then there's diurnal, which means that that location has only one high and one low tide each day. Then we have mixed semi-diurnal, meaning that there's two unequal high and low tides each day. Now, these patterns are represented in the graphs below, and if you ever pulled up a tidal chart, you'll probably notice some of these very similar types of tidal patterns and waves represented on the charts. Now, if you look at this map, you'll see the global distribution of semi-diurnal, diurnal, and mixed semi-diurnal tides. Now, you might wonder, why are there certain types of patterns in some areas and not in others? Well, I'll give you a clue. First, tides are waves. They're the largest waves on the planet, actually, and they rotate around what we call amphidromic points. This rotation, of course, is obviously guided by the gravitational pull of the moon and to a lesser extent the sun, which we'll get into in a bit. But as the tides rotate around these points, they run into continents and land of various different shapes. The differences in land shape and ocean basin shape and depth will oftentimes dictate how much water can flow in and out of a particular area at a particular point in time, and this is what starts to cause the different tidal patterns. As you might guess, it gets a little complicated, but we've been able to crack it and mathematically predict tides very well all around the globe. So now let's talk about tidal range, and that's the difference between the low water and the high water mark on a coastline. Now, this difference will vary from day to day and from place to place depending on where you are. Now, here in Florida, we're not used to it varying that much. We have usually a difference of maybe 2 to 3 feet on any particularly given tide. Now, as an example of a much larger tidal range, I was out in the Pacific Northwest doing a multi-day sea kayaking trip. And the picture on the right shows our kayaks laying on this bed of rocks. Well, during high tide, all of those rocks are covered with water. During low tide, I was actually standing taking that picture and I was completely dry. This might have been a difference of about 10 feet or so. Every night when we made camp, we had to make sure we took the kayaks and put them way up into the trees because the changing tides would totally change the landscape. Big logs, even rocks would move around based on the tidal flow because there was so much force. Within a tidal cycle, you'll have a variety of flow rates based on where you are and how much water is coming and going. This is demonstrated in the bell curve here. The top of the curve represents high tide, and that's going to be a slack tide where you don't have a lot of water movement. Towards the bottom of the curves on either side would be low tide, and that again is going to be a slack tide where you don't have a lot of movement as well. In between is where you're going to get the majority of your water flow in and out of an area. And that's where the water flow can really have a big impact on boaters and kayakers and anybody using the water. Now, so far, all I've been talking about is the gravitational pull of the moon. But remember, the sun actually plays a role as well. So twice a month, we have what we call a spring tide. This is when the moon and the sun and the earth all line up in a line, and thus the gravitational pulls actually amplify each other. This occurs during the full moon and the new moon. This is when you're going to see the largest tidal ranges of the month. That means the highest high tides and the lowest low tides. Now, the opposite of this is the neap tides. This occurs when the moon, the sun, and the earth are at right angles to each other. Now, in this scenario, the moon and the sun are going to be pulling at different angles. Thus, you are not going to have as wide of a tidal range. Your high tides are going to be less, and your low tides are going to be a little higher. So they're not going to be as different. This, of course, happens in the first quarter and the third quarter of the moon phases. Now, let's see what this looks like. In this diagram, you'll see at the very top, you'll see the high tides and then the low tides. Notice the high tide for spring tide versus the low tide for spring tide. Now look at the high tide for the neap tides and the low tide for the neap tides. They're more close together. There's not as much of a difference. So this is what the difference is between the spring and the neap tides. Now, beyond the spring and the neap tides, there's a few other factors that can actually play into the tidal range. And those are physical factors like the shapes of coastlines. A big example of this would be like a shape of a river. If the tide is coming into a very narrow opening like a river, all of that water has to kind of funnel through that one point. And that's going to amplify the tidal range. You can even get what we call a tidal bore, where it's almost like a standing wave that pushes into the river as the tide comes in. And in certain places around the world, people actually have gotten into the habit of surfing these waves. This is an example of one such situation in France. And there's been cases of people being able to stay on a board for over 20 minutes riding these waves into the river. However, this effect can occur in smaller bays and inlets as well, any place that's sort of closed off to one degree or another. Another factor actually has to do with storms, and we're going to talk about tropical cyclones and hurricanes in another note set, but as storms or low pressure systems come near shore, they can bring what we call a tidal surge. It's that increased tidal range associated with these strong storms. Now, this is a picture of a tidal surge from Hurricane Matthew in 2016, and you'll notice that water coming all the way and past the condominiums there. Now, Hurricane Matthew was not one of the strongest storms in Florida's history. However, it still had a major impact on the coastal regions because of storm surge. And as the diagram shows you here on the bottom, the higher the category of the storm, the higher the winds, the lower the pressure, the higher the storm surge is going to be. And storm surge can often be one of the most damaging aspects of these storms. Now, if you look at tidal range globally, you'll notice the areas in red and yellow tend to have the largest tidal ranges. And then if you notice, the open ocean tends to have a lot of the blues, purples, and light greens. That's simply because open oceans tend to have very little tidal range. You can also see the amphidromic points, which are sort of the centers where all of the lines are coming to in the oceans. Those lines are basically as the tides progress around in a circle. The farther away you get from those amphidromic points, the larger your tide range tends to be. Now, another thing to think about here is if the continents were in a different position, those points of rotation for the tides would also be different, and you would have a different tidal pattern. Now, if you look at smaller bodies like the Mediterranean and the Red Sea, they tend to have less tidal range as well, very minimal. And then, of course, when you also look at things like large lakes, like Lake Superior, they also show a relatively small tidal range. In these smaller enclosed bodies, oftentimes wind can be a much larger factor in terms of how high or low the water is. All right, now it's time to talk about currents, and that is the continual physical movement of water caused by wind or density. We'll get into both types very much shortly. Now, currents, it's important to note what they actually carry. Obviously, they carry water, but along with that, they carry nutrients, which of course we know is very important because productivity is governed by the availability of nutrients. They also carry dissolved gases such as oxygen and carbon dioxide. They also carry heat. Thermal energy is redistributed throughout the globe due to currents. And of course, living organisms are also transported with these currents, such as fish and turtles, and especially larval forms of marine life. And of course, especially towards coastal regions, sediments can be carried in the water as well. Surface currents are typically driven by global wind patterns. As they move across the surface of the water, they move the water. It's that simple. This diagram shows you a collection of the major currents globally. The red are the warm water currents coming up from the tropics, and of course blue coming down from cooler regions. Before we get too carried away with surface currents, let's talk about global wind patterns and what actually causes wind. Now we know that the Earth experiences uneven heating from the sun. That's why the equatorial regions are warmer than the polar regions. If you look at it in this diagram, you'll notice that the sunlight coming from the sun is hitting a much more compact area in the equatorial regions, whereas around the poles, it's being spread out over a larger surface area, which decreases the amount of energy per unit surface area that's being absorbed. These differences cause certain areas, especially equatorial regions, to become warmer than other areas in different latitudes. Now, I'm not going to get into the extreme specifics here, but it's good to note that atmospheric convection currents generally are the result of this uneven heating. You have areas like the equator where warm air rises. Of course, warm air is less dense. That's why it's rising. As it increases in altitude up into the troposphere, eventually it's going to get cooler. As it gets cooler, it's going to get denser. As it gets denser, it's going to sink in areas of less solar radiation and cooler temperatures. Thus, we form convection cells in the atmosphere, very much like the same cells that form in a pot of boiling water. The results are a series of low and high pressure belts across the globe, from the equator all the way to the North Pole and, of course, all the way to the South Pole. Wind is the movement of that air from a high pressure belt to a low pressure belt. Now, that air that's moving from a high pressure belt to a low pressure belt undergoes a change in direction based on the Coriolis effect. The Coriolis effect describes the impact of the Earth's rotation on something moving across the Earth's surface. Wind, for example, curves clockwise or to the right in the northern hemisphere and counterclockwise to the left in the southern hemisphere. So, using these principles of unequal heating from the sun, convection currents due to the density differences in air masses, and of course, wind moving from high to low pressure, and that movement being affected by Coriolis effect, produces very consistent wind patterns throughout the Earth. It's not important that you know all the little details of each type of wind belt, but the overall idea of how they form is an important concept. Now let's head back to the surface currents themselves. As wind blows across the ocean surface, it's going to create a current. That current is also going to be impacted by the Coriolis effect. Specifically, it will change the direction of the water current about 45 degrees clockwise in the northern hemisphere from the prevailing winds that start the current to begin with. And of course, this would be counterclockwise in the southern hemisphere. There's an interesting characteristic of this as you move deeper in the water. That 45-degree turn is actually going to be amplified with each layer of water as you go deeper and deeper. This can actually end up producing a net flow of water almost 90 degrees from the current itself. We call this pattern Ekman spiral. And of course, the more volume, the stronger the current is, especially the deeper the current goes, the more this will impact the direction of the current as you go deeper. So now let's look at the big picture. Surface currents combine into gyres, or circular systems that span an ocean basin. This circular movement is possible because of the angle at which the wind has been changed due to Coriolis, and of course the degree at which the water has changed direction from the wind direction as well due to Coriolis. Add on top of that the position of the continents, which obviously water cannot go through, and you start to get these circular patterns. For example, in the Atlantic, you have water moving north across the United States, the eastern seaboard, then it heads over towards Europe, and then it starts to go south again towards the equator, completing and fulfilling the circular pathway. There is a consistent ocean gyre in each of the different major oceans. Now let's finish up with deep water currents. Deep water currents are driven by variations in water density. We actually call them thermohaline circulation, which of course in the Greek means thermos is heat, and of course hails is salt. And of course, as we know from our previous studies, the density of water is controlled by temperature and salinity. That would mean cold, salty water is going to sink, and of course, fresh, warmer water is going to rise. Now we can actually tie all this together into what we call the global conveyor belt, which is going to make a little bit more sense in a few minutes. However, this dictates the really movement of water through the entire global ocean. So let's start with the formation of the deep water in the North Pole and the Antarctica region. As water freezes into sea ice, it leaves the salt behind. Salt basically doesn't freeze. Cold, high salinity water downwells or sinks. That forms the bottom water that then moves south through the Atlantic Ocean towards the Antarctic, where it picks up more cold, salty water. Now this diagram shows you the entirety of the global ocean conveyor belt. Now we've just described the formation of the North Atlantic deep water as it moves in the blue underlying current towards Antarctica, picks up more water. And now from the Antarctic, the deep water flow is going to split into two directions. One is going to go towards the Indian Ocean and the other into the Pacific. Now remember, all of these currents are in the deep water, so we're talking thousands of feet down. If we follow that deep water into the Indian Ocean, it's going to move towards the equator. As it does, it's going to become warmer. Warm water is going to rise towards the surface along eastern African coastline. That water is then going to continue as a surface current, and it's going to loop back and start heading south again. Now let's go back from the Antarctic and follow the Pacific deep water as it heads towards the north. Once again, as the Pacific deep water continues past the equator, it's going to get warmer. And as that occurs, it's going to eventually emerge into the surface waters along the western coast of North America. From there, those warmer surface waters will continue towards Australia and into the Indian Ocean. Now, of course, the warm surface waters in the Indian Ocean will continue on back into the Atlantic and then head north towards the pole once again, where eventually, once it hits the North Atlantic, it will sink and become part of the North Atlantic bottom water once again. Thus, we've now followed the water all the way through the entire conveyor belt. This entire cycle might take about 1,000 years to complete. All right, we have just completed water's journey around the ocean basins. So let's turn it back to you. Here's your in-depth question. How have human populations used surface currents over time? Write about it in your notes, and of course, until next time, keep thinking.